All right, hello everyone. Welcome to this week's Large Language Model System Seminar. This week it's our pleasure to have Yuhan Liu to talk about the recent advancement of vCache. So Yuhan is a final year PhD student at the University of Chicago, advised by Junchen Jiang and also Shan. Her research focuses on vCache. In particular, building efficient vCache via cache compression, dynamic blending, and also cross-modal sharing. She's the leader of LMCache project, which we just talked about, and is now an open source, actually the open source vCache layer for vLLM. All right, so you have what's yours?
Yeah, thanks for the introduction, Chen. Today I'm going to present a case for the vCache layer to enable the next phase of fast distributed LLM serving. So to start with, I want to talk about the current trend in the industry right now. So LLM inference currently is really huge. And so as you may know, only about 10 companies are dedicated to training new LMs. However, millions of applications and organizations run LLM inference now. So as Jensen Huang also said, the significant computational requirements for inference scaling now surpass the pre-training compute demands. And to solve the inefficiencies in LLM inference systems, there are tons of research ideas arise, both in industry and academia. So that includes disaggregated prefill, which separates the prefill and decode phase on different devices. And that also includes vCache sharing, which reuses vCache across different queries. And also fault tolerance, which migrates vCache to other healthy nodes if one fails. And there are a lot of research, as you may know, about MOE, such as DeepSeek, and finally about RAG, which retrieves relative documents based on user queries. So key questions here we have saw this like industry and academia proposals all seem to propose their own designs and implementations for different optimizations related to like vCache, inference, etc. And the key question here we want to ask is what's a common component needed by these ideas? And our answer to this question is vCache layer, we find is a key missing common piece across all these proposed ideas. So just a brief introduction of what vCache is. So vCache is actually a three-dimensional tensor for any input prompt. And here, for example, if we have a prompt is tomato a fruit, and for specific transformer layers, it has a two-dimensional tensor, and so basically for each each token in the input, there is a corresponding vector to that token, representing what LLM learned from the input prompt. And so this is one layer's vCache, and there are many layers in the transformer in the whole LLM. And this like whole three-dimensional tensor will be used to this vCache is actually generated during the prefill phase of LLM inference, and the vCache as an intermediate output will be used for generating new tokens in the decoding phase. And so in this talk, I want to talk about better vCache management for LLM inference. And so it's actually the layer below the serving engine layer. So I actually look at your schedule in the for this class, and I saw you already talk about vLLM, and there are also other popular serving engines such as SGLang, TensorRT. And so in this talk, I'm going to talk about the layer below the serving engines, which is a KV cache management layer. And like you have already talked about like the page attention mechanism, which manages KV cache inside the GPU cache. And today I'm going to talk about a better one that can manage KV cache across different storage layers. So today I'm going to talk about LMCache, which is a KV cache software library for production use. And you can reach 3 to 10x delay savings in a lot of use cases, including RAG and multi-run QA. And what's the most exciting about it is that you can store KV cache of reusable text across various locations, including GPU memory, CPU, local disk, or remote disk. And it's adopted by many industry companies, and they actually give a lot of useful insight for us. And in this lecture specifically, I'll talk about I'll focus on the preview optimizations inside LMCache. And the first one I'm going to talk about is Shan, which compress the KV cache into compact bit streams to transfer KV cache across different nodes. And so to start with, I want to briefly talk about what's preview. So preview in LLM inference. So basically, LLM inference has two phases. The first one is the preview phase, which takes in the user prompt as a whole, and then generates a KV cache of it, and then it gives to the decoding phase, which takes in the KV cache and the first generated token to generate the second token. And similarly, to generate the third token, it takes in the second token and the KV cache for all the previous tokens. So a challenge in this preview phase is that if we have a long prompt, like a long, for example, a document that that encodes a background knowledge of the input. For example, if the user asks the LM to write a PyTorch code, then the user may input like a PyTorch documentation for the LM to understand. And in that case, like the time to prefill the context is really long. Here, this is an example. It can take about 10 seconds to prefill a very long input. And that can lead to very long response delay and bad experience for end users. So like a lot of prior work has already been like using KV cache to accelerate this like long prefill delay. And here, if we load the original KV cache from a remote device to the current GPU server, then that can take actually even longer time than the original prefill delay. So the user will also like have a very long long response delay and bad experience. And here for caching, what we want to do is to reduce the size of the KV cache to reduce the prefill computation and also the loading time. So what we do is instead of prefilling the original input text, and instead of loading the original KV cache, which can take a long time to transfer it across the network, and instead we load the compressed KV cache and perform some decompression operations on the GPU, and then we can greatly shrink the total like the total loading delay and the prefill delay. So this is a workflow of how prefill with compressed KV cache works. So given the original KV cache produced by the LLM at some point, we compress it and make it into B streams and then store these B streams inside the storage devices. And whenever the KV cache is needed again, we load the compressed B streams from the storage device back to GPU devices. And then we perform GPU-based decompression to make the B stream back to the tensor format. So I'll start with the compression part of cache. And a key insight here we use is instead of moving the tensors on the network, we move the B streams. So there are a lot of prior work right now, especially in the machine learning community, that performs quantization or token dropping to shrink the tensor size of the KV cache. However, since we mainly want to reduce the time to load the KV cache about network, then it gives us more opportunity to make the KV cache into B streams. And that can potentially give us higher compression efficiency. And for caching, we actually utilize three KV cache specific characteristics, and which I will talk about in the following slides. So the first opportunity we use is that we find nearby tokens have similar KV cache vectors. Here is an illustration in this. So here for different tokens and the same dimension, and we call it channel, here we have pretty similar numerical values for nearby tokens. So we did a quick empirical study on this, and here we plot both the original distribution of KV cache and the delta tensors between nearby tokens, which is the red line here. And we can find that the red curve is actually much skewer than the regional distribution of KV cache. And there are some prior works in the theory community that shows like a skewer distribution can be easier to compress. So in caching, what we do is given a layer or a channel's KV cache, K or value cache, we divide it into several chunks. And then for each chunk of tokens or each group of tokens, we use the first token as the anchor token. And then for later tokens, we compute the delta tensors of basically subtracting the first anchor token from the later tokens. And then we'll get this delta tensors, and we compress delta tensors and anchor tokens separately. So the second opportunity we use is we find different layers have different sensitivity to compression errors. And to verify this, we did a lot of empirical study. And basically what we find is, for example, as you can see here, the x-axis is a layer group, and the y-axis is LLM output accuracy. And we can see here, if we apply the same amount of rounding error to different layer groups, earlier layer groups have much more impact if they apply the same amount of error. And this guides us to apply different levels of quantization to different layers. And here we use, for example, for a Llama AB model, which has 32 layers in total. We divide it into 3 groups and then apply 8 bits to the first layer group and 6 bits to the middle, and finally 4 bits to the last layer group. And so before the last step, we actually still keep the tensor format of the KV cache. So how to compress it into bit streams? Here we use arithmetic coding to encode the KV cache tensor into bit streams. So just a brief introduction of arithmetic coding. Arithmetic coding represents the whole input message as a single number between 0 and 1 by progressively narrowing an interval based on the input's probabilities. And there is an important property in arithmetic coding is that if the probability distribution is more skewed, then the output will have a much higher information gain, which leads to a smaller size, basically. So how can we do arithmetic coding for KV cache? A key insight here we find is we find grouping the KV by channel and by layer is better than other groupings. And in this figure, the y-axis is a bits per element, which is smaller the better. And basically, the arrow here shows the information gain, the larger the better, for grouping the KV cache by different granularities. And here, this shows the information gain of grouping KV by token, by channel, and by layer. And we can see that the information gain of grouping by their channel or layer is actually much larger than the information gain of grouping by tokens. So to perform arithmetic coding in KV cache, a naive strawman, as you can see here, is we can put every element in the KV cache together and then do arithmetic coding. And this basically makes the whole tensor as a group. And we actually observed that the whole KV cache have very different values. So that makes the whole distribution really uniform. And that's not good. So what we do is we split the KV cache into many groups, where each group contain one layer and one channel, and that makes each group very skewed, like in distribution. So just a summarization of caching compression. So first, caching compresses delta tensors instead of the original tensors. And then we perform narrowwise quantization where we apply more aggressive quantization to later layers than the earlier layers. Finally, we apply smart arithmetic coding to make the KV cache tensors into bit streams. Yeah, so I want to pause here to see if there are questions from the audience. You may wonder whether there are decompression overhead to make the bit streams back to the tensor format. And the answer is yes, it's actually pretty slow to decompress the bit streams back to tensor format with arithmetic coding. So to solve this overhead, to reduce this overhead, we implement GPU-based decompression with customized CUDA kernels. And furthermore, we also pipeline the loading of KV cache with decompression. And for example, when we are loading KV cache for the second chunk, then we can start the decompression of the first chunk. And this is what we do with caching's decompression. So just a brief overview of the evaluation for caching. So here this will only show a very small subset of it, and you can take a look of our full paper for more results. So here we use the long chat dataset for accuracy measurement. And this dataset basically tries to ask the topic in a very long context. So, and we use the network bandwidth we use here is 3 Gbps. And to host the model, we use 4 A40 GPUs with tensor parallelism to serve this Llama 2 70B model. And the system metrics we use includes the size of KV cache in megabytes and time to first token, which is the total prefill delay that includes the time to load KV cache from storage device and the time to decompress it and prefilling the new user question. So here in this figure, the x-axis shows the size of KV cache and y-axis shows the accuracy. Here, this is a quantization baseline which applies the same level of quantization for all the layers. And this is where caching is at, and we can see we can have about 4x reduction in size of KV cache. And on the right-hand side, this shows the time to first token on the x-axis, and y-axis shows the accuracy. This is a quantization baseline, and this is where the naive prefill is at, where we just recompute the KV cache for the given input. And this is where caching is at. We can see that we can have about 3.7x improvement in TTFT. And so the reason why the TTFT has less improvement than size is because of the decompression overhead. And in this figure, we shows how caching reduces prefill delay under different bandwidth conditions. The x-axis here is the network bandwidth to load KV cache, and y-axis is the TTFT. And here, this shows the prefill delay, and this will not change across different network bandwidths because it's basically takes zero time to load the text from the remote device. However, it will still spend the same amount of GPU computation on GPU, regardless of the bandwidth. And this is where quantization baseline is at. And this is where caching is at. We can see that with bandwidth increase, we can have only a small amount of absolute TTFT gain. However, we can still have gains in storage size, so that we can, since caching further compress KV, like it has much better compression efficiency. We can basically feed much more KV cache for a fixed storage budget. And finally, we also apply caching upon two very popular token dropping method from the machine learning community. We can see that here the H2O is a technique that drops unimportant token from the KV cache. And for LLingua, this drops unimportant tokens from the text prompt itself. So for both methods, we can still apply caching's compression to make the KV cache into compact bit streams. And here we can see that we can still have a lot of compression gain from it. So with that, that's all about caching. Any questions from the audience? Okay, if not, let's move on. So for caching, we and also all the prior work actually for in KV cache sharing, there is a very strong assumption behind it, that is KV cache can only be reused if the it's coming from the same model. And in this the next part of the talk, I want to talk about our paper Joy Speak, which takes the first step to share KV cache across different LLMs. And here we focus on LLMs, different fine-tuned LLMs based on the same foundation model. And so to briefly talk about the background. We find multi-LLM serving is everywhere. So there are many scenarios where multiple LLM can coexist in an LLM system. For example, in multi-agent pipelines, a coding agent may first generate code for the user based on the user prompt, and then give it to the testing agent to test to see if there's any bug in the code. And if there is, the debugging agent will take the code for debugging purposes. And in this scenario, different agents can be powered by different models, fine-tuned for specific coding needs. Also nowadays, chatbot applications such as ChatGPT periodically update the model with newer data. And in this case, multiple models also may coexist in this inference system. And a very huge inefficiency in this multi-LLM serving system is that different models often share the same input context. However, the same input context is always recomputed because KV cache sharing has always been like used for models different the context across the same model across different user prompts. And for example, this scenario may happen when a user goes to like a ChatGPT user goes to a session like several months ago to query the LLM for some newer questions. And in this case, since it's the model has already been updated, they may the model A and the model B may look at the same conversation history to answer users' question. So the goal of our paper Joy Speak is say we have the sender model and the receiver model, which basically the sender model sends say conversation history or like the same documents to the receiver model. Instead of letting the sender model and receiver model communicating in text form, which can take a long time to pre-fill the text context before decoding, we let the sender model to communicate with the receiver model with KV cache. And to do that, we only need to send the KV cache from the sender to the receiver model and do some kind of translation operation to make the KV cache compatible with the receiver model before decoding. So potentially these can greatly shrink the pre-fill computation for faster response delay. So let's first take a look at the effect of directly reusing another model's KV cache. Here, this x-axis shows different data sets, and y-axis shows the F1 score, the higher the better. Here, this is the original receiver model's accuracy when this on different data sets. And here for the receiver model, we use Mistral Lite, which is a high-performance model specifically fine-tuned on long context. And the original sender model is the Mistral 7B model, which is like a less performant version of it. And here, this is original sender model's F1 score. We can see that it's much lower than the F1 score of the receiver model. So if we directly apply the sender model's KV cache on the receiver model, the accuracy will be greatly degraded. And we actually find this results in a lot of across many model pairs. So luckily, there are actually some opportunities we can use here for KV cache. So the first insight we use here is we find different layers have different sensitivities in KV cache deviation between models. And for example, in this figure, this y-axis here shows different layers, and the x-axis shows different layers, and y-axis shows F1 score. So this different bars shows like if we apply the KV cache deviation error on the receiver model, which is the Mistral Light model, we can see only several layers of it, a subset of layers are greatly affected by the KV cache deviation errors. And we call this these layers that are greatly impacted in quality. We refer to this as critical layers. So this indicates that we can reuse the KV cache for some layers while we recompute the rest. However, a key challenge here is if we do partial recomputation, it's actually not that easy to freely transit from reuse to recompute. Let's first take a look at how normal recompute for one layer works. So first, the input to each layer is input embedding E, and here we call it E cache. It's a two-dimensional tensor, and it has to have the information for all the tokens in the context, and another dimension is a hidden dimension. So the output of each layer is eCache for the next layer's input, which has the same shape. However, if we do KV reuse, the input is the shape of like number of tokens only in the question and by hidden dimension. And also the output of the layer also only contains the KV cache of the tokens in the questions. And this is because in order to have KV reuse to reduce the delay, the input, the eCache has to be a smaller eCache than the original eCache, which contains all the tokens in the context. So this actually disables transiting from reuse to recompute. So what we do is at any transition point from reuse to recompute, we load the eCache of the sender model's eCache. So that is freely used, but as you may know, like it has some deviation because like the eCache of the sender model and the receiver model already has some deviation. So we actually did some sensitivity study, and here the x-axis shows the layer number, and the y-axis shows the attention output error. And so basically for the red curve here, we apply a lot of sender models eCache on the receiver model. And we can see that every time if we reuse the sender model's eCache, that leads to a jump in attention output error. So this shows that more transition points can lead to higher output error. So what we do in Joyspeak is we limit the number of transition points to 1 from reuse to recompute. So just to put it together, if we let different models communicate in text, then every layer here in the LLM needs to be recomputed to get the recomputed KV cache, as marked by this blue KV cache here. And if we, for Joyspeak on the other hand, we skip the recomputation for some layers and only recompute part of it. So say like we only compute like the third and the fourth layer of the the LMs. And for the rest of it, we load the reuse KV cache directly from the sender model. And for the third and the fourth layer, we first load the eCache of the sender model, and then let the receiver model recompute the third and fourth layer of it. And for the rest of the layers, we also load the KV cache of the sender model. So basically, we concatenate this reuse and recompute and reuse KV cache together, and then feed this whole concatenated KV cache to the decoding phase. Here we assume we know which layers we want to recompute. But how to determine this? And this is based, we need our second insight, which we find that the layer-wise error sensitivity is actually pretty consistent across different inputs. And here, for each bar, we apply the KV deviation error between models on that layer's KV cache for different inputs from the HAPA-QA dataset. And here we show the F1 score difference distribution it made on the final output. As you can see here, the variation in F1 score difference actually very little for almost all the layers except this layer 23. And layer 23 is critical layers where using the sender model's KV cache can greatly reduce the generation quality. And fortunately, we also find that most of the inputs for layer 23 are greatly impacted by direct KV reuse, which suggests that we can do some offline profiling based on a training data set to see what's the optimal number of set of layers to recompute. So in JoySpeak, we profile the maximum F1 score that can be attained for each number of recomputed layers on a training dataset. And as we can see here, for the profiling phase, we can get a figure where the x-axis is the number of recomputed layers and the y-axis is F1 score. So basically, we can choose the recomputation config, which contains like the layer to start recompute and the layer to stop recomputing. And we can get this Pareto frontier of the recomputation config. So what we do is we profile this Pareto frontier based on the training dataset and apply this config to the testing datasets. So for the evaluation, we use a long bench dataset as quality measurement. And long bench is a benchmark that contains a lot of long context question answering pairs, and it also has other tasks such as coding completion and context summarization. And here in this talk, I will just show one model pair's result. Here we use Mistral Lite versus Mistral 7B model pair, and we use a network bandwidth of 17 GB per second. And for the system metric, we use TTFT, which is a total prefill delay, which contains the time to send KV cache over this 70 Gbps network bandwidth, and the time to recompute for better accuracy. And the quality metric we use is F1 score. So in this figure, we show the prefill delay versus F1 score, and this is where the original full prefill is at. And this is where JoySpeak is at. We can see that JoySpeak can greatly reduce a prefill delay without losing F1 score. And this is where direct KV reuse is at. And for this baseline, it only needs to send the KV cache from the sender to the receiver model. However, it can greatly reduce the quality because it doesn't consider the layer-wise sensitivity in KV cache deviation error. And similarly, we can see similar results for other datasets. We have 8 model pairs in total in our full paper. Feel free to check it out. So with that, that's all about the second part of the talk. I want to pause here to see if there are questions from the audience. Last part of the talk, I want to talk about cache blend. So both Joyspeak and Cache actually assumes, and many prior works assumes that only the prefix cache can be reused. However, like in real practice, for example, in RAG systems, like the context that can be reused is likely not the prefix of the input. So to solve that, I participated in a work cache blend, which also won the Best Paper Award for this year's EuroSys, which tries to blend different KV cache for different chunks in RAG to reduce inference latency. And to start with, I want to talk about like how RAG system work. So basically for RAG, given a user question, like the RAG retriever will find out the related documents to the user question. And then the different documents will be concatenated as a whole to feed in the LLM inference engine. And finally, the LLM inference engine will inference based on the concatenated context to give an answer to the user. And a key inefficiency in RAG system is that, as you can see, RAG concatenated context from multiple chunks to be fed into LLM. And this can lead to long prefill delay because like there are multiple chunks of the documents, and it can grow very long input, and this can lead to very long prefill delay. So let's take a look at why existing solutions cannot work. First, if we do prefix caching as prior works do, this is inefficient. For example, we assume that there is a query and we need two documents to answer the question. And let's assume that LLMs have already seen these two documents separately and stored their KV cache inside the system. However, in this case, only the KV cache of the first document can be reused because the second document is no longer a prefix, thus it has to be recomputed. So basically, the system still need to recompute the document 2 here. So this means that even though we have 100% of the cache that live in the system, only 50% of it can be reused. And the heap rate can decrease as more documents are retrieved. So people will naturally wonder, like, why don't we just put KV caches together since we already have the KV cache stored in the system? And this doesn't work because naive concatenation or full, we can call it full KV reuse, actually gives us very bad generation quality, as you can see in this figure. And so why does naive concatenation fail in this case? The answer is that it misses the cross-attention between documents. So on this figure, this shows the attention matrix after we feed the document as raw text to the LLMs. For example, as you can see, this 18th row and 7th column shows the attention or the so-called semantic correlation between the 7th token, which is in the document 1, and the 18th token, which is in document 2. So now we show the attention matrix with full KV reuse. And as you can see, by comparing the left bottom part and of the two attention matrices, full KV reuse completely ignores the cross attention between two documents, which is exactly the reason why it gives bad generation quality. So in cache blend, we tackle this problem by selective recomputation. That is, we recompute a small subset of the tokens in the second document in a way such that the most important cross attention can be recovered. And in this way, as shown here, the generation quality can be maintained while most of the KV cache can still be reused. So for our system, if we start with the same user query and the retrieval process, then we have a KV cache loading controller that stores and retrieves KV cache from external storage. And the benefit of such storage extension is huge because for every copy of the KV cache we saved, we can always achieve a 100% cache hit as long as it can gonna be reused in the future. And then the loading controller retrieves the KV cache for the 4 documents here. And another component, KV cache blender, will blend the KV cache and make the fuse KV cache feed that into the LLM inference engine to give a high quality answer to the user. So the first part of KV Cache Blender is about how to recover the positional embedding. In normal LLM inference, the KV cache will always go through a position embedding called like the rotary position embedding, such that the KV cache could be changed at different positions. And in normal prefill or prefix caching, the KV cache will always be stored with a position encoding at fixed positions. However, since for cache blend, we may need to change the order where like the KV cache is being recomputed, being computed before. So this motivated us to store the KV cache before the position encoding and then recover the encoding on the fly when we know where the KV cache is reused. So let's see how cache blend performs selective recomputation on high level. Let's first start with normal prefill or known as the full KV recompute. So we start with the input embedding on layer, say layer I. In this case, we have 8 tokens in the input, where each column corresponds to an input embedding for a single token. Then from this input embedding, the QKV matrices are generated. And the QK matrices are first multiplied together to give this attention matrix. And then the attention matrix is further multiplied with this V matrix. And then from that, we can have the input embedding of the next layer. And the compute complexity here is the order of total number of tokens in the input. For our selective recomputation, assume that we only compute 2 out of the 8 tokens. Then the input embedding will be smaller, only having 2 rows. We then have a smaller QKV matrices, and so we can already reuse the KV cache for the other 6 tokens. And here we got this updated K and V matrices. And then the smaller Q will be multiplied with a big K matrix to give a smaller attention matrix. And finally, by multiplying the attention matrix with a big V matrix, we can have an input embedding of the next layer. And in this way, the compute complexity will be reduced from the total number of tokens to the number of selected tokens. However, a question is, you may wonder like how to select the tokens to be recomputed. With that, we have the first insight that we find that the fraction of high KV deviation tokens is small. In this figure, the x-axis shows KV deviation while y-axis is a CDF. So the definition of KV deviation is given here, which is very simple. It's just the L2 norm difference between the pre-computed KV cache and the recomputed KV cache. As we can see here, the fraction of high KV deviation tokens is small. So in this figure, we show the effectiveness of recomputing high KV deviation tokens. The x-axis here is a fraction of recomputation ratio, where the recomputation of high KV deviation tokens are always prioritized. And the y-axis is output attention deviation, which measures the attention between the context, documents, and the user query. Further, the definition of the output attention error deviation is shown here. As we can see in the figure, recomputing a small fraction of high KV deviation tokens are greatly reducing the output attention error. However, we cannot get the KV deviation for all the layers since we need to have the fully recomputed KV cache. So this requires our third insight. Looking at this figure, the y-axis is the Spearman ranks correlation of the KV cache, and the x-axis is the layer pair. For example, the first column is a Spearman correlation of the KV deviation between the 5th and the 6th layer. And we have 12th versus 13th and etc. Here we provide the definition of the Spearman rank correlation. It looks complicated, but we can use a very simple example to illustrate. So say the rank of the KV deviation layers for a specific layer L is 1, 2, 3, 4, 5. And this means that the first token has the highest KV deviation. And on layer L plus 1, the rank is 2, 1, 3, 5, 4. Then we can have N, which is total number of tokens, and D is simply the difference between the two ranks. And so we can see that like the KV deviation, high KV deviation tokens are actually similar across layers. And this means that we can use the KV deviation for the first layer as a prediction of KV deviation at later layers. So in practice, what we do is we only recompute the first layer's KV cache, and then look at the recomputed KV cache at the first layer and compare that with the original, just simply concatenated KV cache. And then we can decide which important tokens to recompute for all the later layers. Finally, we have this loading controller where we pipeline compute the recompute of the important tokens and the loading of KV cache from disk to pin CPU buffer pool and from the CPU buffer pool to GPU memory. So in this case, loading delay can be completely hidden by the recomputation process. So just a brief walkthrough of the evaluation setup. Here we use the 2WikiM QA dataset where we retrieve top 6 chunks, where each chunk has 512 tokens in each chunk. And we use 1.5K sample queries, and we use a Llama 70B model hosted on 2 A40 GPUs. And initially we just stored all the KV cache chunks needed by the queries on disk. And we just send the request to the request queue at a specific rate. And we look at the full recompute, full reuse, and prefix caching as baselines. So here in this figure, the x-axis is TTFT, which includes the time to load KV cache from disk and the time to do recomputation. And y-axis shows the F1 score. Here is where full KV recompute is at. This is basically the naive prefill where we take the concatenated text as an input for the LM to process. And this is where KV reuse is at. This can greatly drop the F1 score since it doesn't consider the token importance. And this is where caching, prefix caching is at. We can see that it can only reduce TCFT by a very small amount because we have 6 chunks in total, and it can only reuse only 1/6 part of the input. So that only saves a small amount of prefill computation. And this is where cache blend is at. We can see that we reduce TTFT by 3x. And we also tested cache blend throughput. And here we can see that we can have 3x higher throughput compared with the best baseline, which is prefix caching. So with that, that's all of the 3 parts in my talk. So we have looked at how to quickly transfer KV cache to GPU memory and how to reuse the KV cache of the different LM. Finally, we look at how to reuse non-prefix KV cache by quickly combining KV cache of multiple chunks. And with that, any questions for cache blend?
Yeah, I guess let's first of all thank the speaker. Peter.